Good morning. Last time we considered the event whether there is rain on Friday morning at 9 a.m. in Oxford. Now, we kind of thought it's either that or it's the complementary event that there is no rain. Mathematicians like to simplify things. Now, I have to leave to your judgment whether you thought there was rain or not this morning, because somehow it was pretty miserable, but I certainly didn't catch very many drops of rain. But that's not really the point of probability. The point of probability is that we can set up models, and we can do calculations in models that are informed by the real world, but really the connection to the real world is done by something that we refer to statisticians for in some way, well, or to the third term where you learn some statistics, some of you. So the context that I gave last time was the context of a probability space, which allows us to formalize things that we may think of in the real world. We have the special case so far where all outcomes are equally likely, and in some way the example with the weather forecast does not fit that bill, because we trusted the Met Office that there's an 80% chance of rain. That is, the probability of rain is 80% and leaving only 20% for the probability of no rain. But that framework is what we are going to generalize today, and in particular where we will be able to then get back to that simple idea of rain or no rain in that framework. Now, we had some other discussions to do with counting, because lots of things, particularly when it's about equally likely events, is about counting how many things belong to the event whose probability we want to calculate. And so permutations were a basic combinatorial object, and then the way of arranging distinguishable objects, we generalized it to the number of ways in which we can arrange objects, some of which are indistinguishable, and then we saw that we had to divide through by these factorials of the multiplicities of the distinguishable objects to get a more general answer to the question, how many arrangements are there to arrange these n objects. A particularly important special case is the binomial coefficient, which you will have seen in other contexts, or related contexts, I suppose. And we will have two more examples today about these binomial coefficients. Now, what I meant to write as well here is that after today, you can do problem sheet 1, and you should do problem sheet 1, even though your deadline may be after our next lecture. It's always good to stay a bit ahead of the game and do it now, because it only relates to what we covered or cover in the first two lectures. So it's useful, in fact, to do the problems in the context of lectures. That focuses your mind in the way that we want to proceed here. So yeah, I've already said we want to have some more examples today about the binomial coefficients, and then I will set up the axiomatic approach to probability in the generality that covers everything you want to do in probability, in principle, but in a rather abstract way. So there will still be plenty to say afterwards how to make use of the formalism, or indeed how to cover the formalism somewhere in the background where it is not as important as you may feel after today's lecture. So here is the first example about binomial coefficients. Well, I tell you it's about binomial coefficients, but the question is, how many distinct solutions are there to an equation? And this is the equation where I want x1 plus x2 plus etc. plus xm to be equal to little n, where, of course, there will be infinitely many solutions for the x's if I don't put constraints on, where the xi are something we can count, namely non-negative integers. Okay, doesn't look like binomial coefficients in the first instance, and that is actually instructive, because sometimes you just have to think, can I rephrase the question in a way that it involves the structures that we have already understood and dealt with. So here is the solution, or one solution, I should say. We can recast the question as balls in boxes. Suppose we have m boxes and n balls, then the xi can represent the number of balls in the ith box for I from 1 up to m. So how do we then count numbers of balls in boxes? Well, what does that look like? It kind of looks like we've got all these balls, and what does it mean for them to be in boxes? Well, it means we kind of separate them. The boxes are numbered 1 up to m, so we might as well think left to right. And so we can kind of think of these box boundaries, if you like, and say if I put m minus 1 vertical lines and n bullets or balls onto the page, then that corresponds to exactly one solution to the problem, namely here you'd have x1 equal to 2 balls in the first box to the left of the leftmost line. Then we have x2 equal to 3 balls in the second box. Then there is this 2 lines next to each other with no ball in between, which we interpret as x3 being equal to 0. And finally, we have x4 equal to 2 balls. So here I've got 7 balls in 4 boxes. So for example, n equal to 7, m equal to 4 would be this. And in general, we can now consider, maybe I should say in general, consider n bullet symbols and m minus 1 vertical line symbols. Right, these are now n plus m minus 1 objects. Okay, and we have our interpretation of how this relates to solutions to the problem at hand. So we can now say in the general framework, the vertical lines separate the bullets into m groups. Okay, and then we just say what is xi in that framework of vertical lines and bullets. Let xi be the number of bullets in the mth group, ith group, sorry, ith group. Okay, I should probably say ith group and then specify that I runs between 1 and m. Okay, so does that help? So far I've just recast the problem into a different problem of a familiar kind. We have these objects. They are of 2 types. And so, so this is asking how many ways are there to arrange these objects into an order, how many distinguishable ways. And so there are n plus m minus 1, choose n ways to arrange the objects. Hence, n plus m minus 1, choose n ways, or solutions, I called them, to the equation x1 plus x2 plus etc. plus xm equal to n. Okay, so the method that I've used here we can call bijection. If you want to if you want to count numbers of elements of a set and you find a bijection to another set, then you might as well count the number of elements of that set instead. Specifically here, every solution to our equation corresponds to precisely one way of arranging the symbols bullet and vertical line, and vice versa, every way to arrange the symbols bullet and vertical line corresponds to precisely one solution to our equation. So we've really been counting the number of elements of the set that we wanted to count. Okay, here's another example. An example that more explicitly has binomial coefficients in it. It's sometimes referred to as van der Monde's identity. And the claim is a certain relationship between factorials for m, n, and k greater than or equal to 0, that is non-negative integers. We have m plus n choose k equal to the sum j from 0 to k of m choose j into n choose k minus j. I'm not sure, did I use the choose language last time? I have a feeling that I may not have introduced that. Say n choose m. Okay, so here's a claim, and there's one thing that I should make precise, because we were thinking of having ways to choose from n objects, choose m of them. Well, in this formula, in the generality written, it may be that the number of elements we want to choose is greater than the number of elements we are choosing from, in which case we have to extend our definition in the natural way and say, well, there's no way of choosing a larger subset from a smaller set. So where we understand that m choose j, or indeed n choose k minus j, is 0 if the bottom entry is greater, strictly greater than the top entry. Okay, with this convention we can set about proving this, and there are different ways in which you could try to prove this. Some of them are nastier than others. 3 variables in principles on which you could do an induction, but I'm not to choose any of those. I'm going to give you a completely different argument. I'm going to give you an argument that, in fact, again, recasts the problem in a different setting, where you can interpret the answer in 2 different ways, one giving you the right-hand side, one giving you the left-hand side. But as it's the answer to the same question, the 2 have to be equal. So the setting here is what are we choosing? We are choosing k object out of m plus n. What are we choosing here? Well, we are choosing j object out of m and k minus j objects out of n. So altogether, we are again choosing k objects out of n plus m. Just that we've insisted that j are chosen from those m and k minus j are chosen from the other n. Right? And then we are summing over all the ways in which we can distribute those k onto the two sides. Right? That's a kind of reasonably mathematical way of looking at this. It's nice to have a story with it. We could imagine that we are trying to form a committee of k people from a group of m plus n people. Now, we need an interpretation here. Maybe this is in a college setup where you have m undergraduates and n graduates or postgraduates. And so you then have lots of ways of choosing committees, and in each choice you will have a number of undergraduates and a number of postgraduates. And if you say, suppose we have j undergraduates, then you choose j of your m undergraduates and then k minus j of your n postgraduates. That gives you all the ways of choosing a committee in which you have j undergraduates. But then you say, I want to count all committees I can form, no matter how many undergraduates. So you're just summing over all the possibilities for the number of undergraduates. And then your right-hand side gives you all the ways of forming a committee of size k from a group of m plus n students. OK, let me write that down. Imagine choosing a committee of size k from a group of m undergraduates and n postgraduates. There are n plus m choose k ways to do this. And if we fix the number of undergraduates first, I should say on the committee. That can be some j in 0 up to k. Well, if you fix j, then we can count how many ways there are to build a committee of that type. There are m choose j ways to choose undergrads and n choose k minus j ways to choose postgrads. Right, and any combination of those are possible. That's why we multiply. And gives you a distinct committee. OK, well, let's maybe write down the conclusion. So there are m choose j times n choose k minus j in total and summing over j gives the result, namely another way of counting all ways of forming a committee. Okay, so on the problem sheet, I think the story is already there, but you will use a story to prove another relationship between factorials. So there is good reason, therefore, to reconsider examples in lectures when you're doing problem sheet questions, because there are hints that are not explicit often, but that you can figure out just by revisiting your lecture notes when doing problem sheets. So let me move on to the axiomatic setup that generalizes the notion of a probability space, as we will call it, from the equally likely outcome setting from last time to the general setup. So here is the axiomatic setup. Those of you doing analysis may have already had a lecture on axioms. They're different axioms, but you may well wonder, are there any advantages of doing those problems next to one another? Because in some way, the game of solving some exercises in the context of axioms is a rather different exercise from what you may be used to, because you're doing things with both hands behind your back in some way and only using explicitly some very basic rules in order to derive some other basic statements. And so do compare what analysis is doing on axioms of real numbers or even natural numbers, I think, and what we in probability are doing on the axioms of a probability space. Of course, you don't need the analysis side to do this. They are completely different sets of axioms, but it's just the idea of an axiomatic setup that is common to both. So here is the definition of a probability space. I've already introduced most of the language. Not sure I wrote probability space explicitly, but if I say that this is a triple, which contains an omega as first ingredient, that's familiar. It's a set of outcomes. An F, which we haven't seen, but which is a collection of events, which I said subsets of omega are called events. And a function P, which assigns to every event a real number. Then you can kind of see, yeah, that's somewhere where we've already done all three of them, but where we need to just be a bit more precise about the connection now. So what have we got? We've got omega is a set called the sample space, or space of possible outcomes. F, we were a little loose last time about what subsets we want to call events, and here we are a little more general and precise in that we are saying F is a collection of subsets, not necessarily all subsets. Subsets of omega. And those subsets that we include in F, we refer to as events. And we have to insist that some properties are satisfied. And those are the first axioms, F1 up to F3, that I will state below. Let me first complete my triplet here by saying what P is. So P, let me write in words, is a function from F. F is a set of events. So if we have a function on F, that means for every set of events, no, for every event, we want to assign something here to R. So we are assigning a real number. And again, certain axioms need to be satisfied. And these are axioms that I'll call P1 up to P3. And again, I'll state them below. Now, you may be used to functions from the reals to the reals, and this is functions from some rather more awkward set, a collection of subsets. But what it means is what I wrote last time pretty much, that you have to assign for events a probability, and that's something very natural in probability. So maybe I should say what this function does is specifying P of A as a real number for every A that we have in F. Okay, so that's our three objects that I haven't fully said what conditions we put on them, but I've said they're a set, a collection of subsets, and a collection of probabilities of these subsets. So here are the axioms. So if 1 is just saying the whole set should be an event, we want to, in fact, assign a probability to the set of all outcomes, and that probability clearly ought to be 1, because we are conducting experiments where one of the outcomes will occur. F2 is saying if A is an event, then A complement is also an event. Okay, so we're just putting some constraints here and say that we can consider events that relate back to other events as members of F. And this is for taking complements. And F3, well, F3, let me do it in two parts here, because that'll allow us to be a little bit more basic in our first references back. So, so if A and B are both events, right? They are sets. So we've already taken complements. We can also take union of A and B, and we want to have collections F for which whenever A and B are events, then also A union B is an event. And F3B is just a little generalization which we need if AI is in F for all I greater than or equal to 1, i.e. I 1, 2, 3, etc. So natural numbers. Then we want to also be able to take unions over these infinitely many, but countably many, as we will call this events. So the grand union from 1 up to infinity of the AI should also be in F. Right? And if you compare with the notes, you will find that this is slightly different in the notes, and so I will comment on that later. But this is entirely equivalent, as you will be able to confirm when you see both next to one another and are comfortable with the notions involved. So these are the axioms of F, and in some way parallel to the axioms of F, we have the axioms of P, and they are there really for things to make sense. This is kind of maybe a little bit arbitrary and probably best seen as preparing the axioms of P. So P1 is saying the probability of an event should always be non-negative. In fact, we want probabilities to lie between 0 and 1, but one of the maybe awkward things with axioms is that we are trying to be minimal and not put more constraints than are strictly necessary, and we will be able to derive from the other axioms that every probability of an event is actually also less than or equal to 1. And that largely depends on this second axiom here, because the probability of omega has to be 1, meaning one outcome has to occur. And then we have P3a and P3b, which kind of hook onto those F3a and F3b. So F3a is saying if a and b are in F, and a and b are disjoint. I defined this last time. But let me recall here, A intersection B is the empty set, no common members. Then what should the probability of A union B be? Well, if there are no common elements, and you are saying the probability that this set of outcomes occurs and the probability that this set of outcomes occurs, well, the probability that either of them occurs is going to be the sum of the two probabilities. And that's what we require this function f to satisfy. So then the probability of A union B is probability of A plus probability of B. Okay, so we could do this because of axiom F3a, which says that for two events, the union is also an event. So this left-hand side is actually well defined. We have taken a function P on F. So this A union B in F means P of A union B is meaningful. So now the generalization is what you may expect here. We are dealing with unions of infinitely many events here. So if AI is in F for I greater than or equal to 1, and they are disjoint. But we need to be a little careful here, because we really need to have the intersections empty for any pair of I and j. Well, if we have that, then the corresponding formula holds that the probability of the union of these disjoint events, which this union is an event because of this F3b, well, that is in fact the sum I from 1 to infinity of the probabilities of AI. Okay, now I've kind of hidden what I had above from last time. In the simple case where all outcomes are equally likely, we just wrote the probability of A is the number of elements of A divided by the number of elements of omega. That is one way in which a function P can be defined, and you can check that these axioms are satisfied for that one. But here what we've lifted is the requirement that we have all outcomes equally likely, and we've even lifted the requirement for omega to be finite. This is very general now. We can allow countably infinite omega. We can even allow uncountably infinite omega, as long as we can then continue to specify a collection of events f and a probability function p. Then we have another example of a probability space. Okay, so we've got the axioms up here. I think I can write a little bit down here without covering things up. So just what I've already said about the numbering here. Well, I've said that the lecture notes do things a little differently, but here is another remark on that. So I numbered them in this way, in this slightly strange way. with A's and B's because they relate so how can I say, because in fact the A part kind of follows from the B part. So P3 of A and F3 of A can be deduced from P3 of B and F3 of B, but not vice versa. That is, we cannot derive the infinite case from the finite case, as it were. And that is a rather more subtle statement, that it can't be done the other way around. But this is kind of the way that you can think of these as really being the same axiom in different incarnations. So yes, so the reverse is not true. More generally, we could write unions I in I for unions where I equal to 1, 2 corresponds to F3A and I equal to 1, 2, 3, etc. corresponds to F3B. Okay, and I think that's what we have in the notes, that we have some more general countable index set, and at some point I'll go into what this countability means and how we can align these things. But as I said, one reason to split things up in this way for now is that we want to get familiar with the axioms, we want to do something with the axioms, and it is very useful to have this special case written out in full rather than as a special case of something very abstract. So what can we do with axioms? The point of axioms is to be general and to be able to apply things to lots of situations, but this is only useful because some things can be done in this generality. And you may already wonder why I've included some things but not others in the axioms. And the answer to those questions is usually, because we can derive what you would have liked to see already. We can derive that from the axioms as stated. So here's a theorem that collects some of those things that you might think, or maybe that should be an axiom too. So let omega fp be a probability space. I said something about unions. If A and B are events, then the union is an event. Well, what about intersections? If A and B are events in F, then the intersection A intersection B is an event in F as well. It's not an axiom, but we will prove that it is a consequence of the axioms. So if A is in F, then we know A complement is in F, and so it is meaningful to talk about the probability of A complement. And, well, if A doesn't happen, then A complement happens, so the probability that A happens, that A complement happens should be 1 minus the probability that A happens, and indeed that follows from the axioms. And then 3, if A and B are events in F, and A is a subset of B, what can we say about the probabilities? Well, you won't be surprised to learn that the probability that a smaller event happens is always less than or equal to the probability that a larger event happens. And again, what you may find intuitively obvious, we can derive it from the axioms. So the thing in some way that's obvious is what's here, but what's not obvious is the axioms, and that's why there's work to do. Right? Why did we specify this, and why is this enough to get everything that we would want to have? And so let's prove these to see how we can proceed without any particular probability space, but with just what the axioms tell us. So for the first one, what are we claiming? We are claiming intersections are in F. So how do intersections and unions relate? We can take complements of everything, and we have De Morgan's laws, and so it's useful to note that our assumption that A and B are in F entail that A complement and B complement are in F as well, and this is by axiom F2. Then we can take unions of events in F, including A complement and B complement, and that union is in F by axiom F3A. And finally, what is A intersection B? Well, it's the complement of the union of A complement and B complement. And so we are again talking about taking a complement of an event in F, and so that by axiom F2 again is in F. Okay. The second one. Well, we want to relate the probability of A complement and the probability of A. What do we learn about our probability function? Not very much, but there is one axiom, namely P3, that relates probabilities of different events. We have two events in our claim. We've got the event A and the event A complement. So the only reasonable way we can get anything out of the axioms is to say, let's look at that union of A and A complement. And then once you figure out how to put things together, you can write a 1 is the probability of omega. Omega is the union of A and A complement, and that splits into the probability of A and the probability of A complement. And what we do with these axioms is we are very precise in our reasoning. Whenever we use an axiom, we refer to the axiom. So this first line is due to that axiom. The second line is due to nothing in particular. It's just the observation that A union A complement is omega. And then the last line is by P3 of A. P3A has a condition. It's not just A and B and F, but it's also that A and B are disjoint. So we have to check that condition and note that A intersection A complement is empty. And that then proves this second claim. So the third claim is about this property that probabilities of smaller events are smaller than probabilities of larger events. So how can we proceed here? So since A is a subset of B, we can write the larger event as a union of A with whatever else there is in B. And whatever else there is something you can write as B intersection A complement. Right? So if you have a set A and a set B that contains A, then what are we doing? We are saying, well, B consists of A and this remainder of B, that is the intersection of B with the complement of A. Okay, so so this shaded area is B intersection with A complement. So that is not just a union, it is in fact a disjoint union, meaning that A and B intersection A complement are disjoint. By P3A, we have a relationship between the probabilities of the events on the board, namely the probability of the union, that is now B, is the probability of the first member of the union, which is A, plus the probability of the second member, and that is B intersection A complement. And we may not know very much about that probability of B intersection A complement, but we do know that every probability of an event is greater than or equal to naught, and that is by axiom P1. Okay, and if this is greater than or equal to naught, well, then we conclude that this probability of B is greater than if we drop that non-negative term on the right-hand side, and that gives us the probability of A. Okay, and so if you look through, we've kind of applied most of the axioms here in order to derive some more statements that you can now use whenever you are working on a probability space. Okay, so I've got 3 minutes, and I said here that the notes are slightly different from what I've written on the board here, and the splitting up of the third axioms in each case into A and B is just a choice that made us write slightly easier proofs here. If you want to relate to the axioms in the notes, then I should give you a brief aside on sizes of sets. You may learn this in other courses, but as you come from several different degree courses, I can't assume that you all see this in a useful way. So it's about infinite sets that we need to talk about sizes. You may have come across notions of countability and uncountability. So an infinite set, S, is called countable if it is in bijection with the natural numbers. That is, if we can count all its elements. So it can be written as S equal to x1, x2, x3, etc. Or we can write this as xi, I in n. Now, there's some ambiguity of whether 1 is a natural number or not, 0 is a natural number or not, and I don't want to go into this. For us, 0 is not a natural number, but it makes very little difference for most purposes. So, otherwise, the infinite set S is called uncountable. And probability works well when you have countable unions, countable intersections, etc. Probability doesn't work well when you have uncountable unions, and that's why we need to have this distinction here. So examples that hopefully you are familiar with, even in the context of countability questions. The natural numbers and the rational numbers are countable. R is not countable. Okay, and then what I've underlined there is that this is for infinite sets. We also say that finite sets are countable, which makes intuitive sense, but the terminology sometimes gets confused. So some people distinguish countable as including the finite sets from countably infinite, which is precise about requiring the set furthermore to be infinite. And that's the terminology that I'm adopting. So P3b talks about what we can call countable additivity. Or maybe I shouldn't say P3b, because actually all of P3 is talking about countable additivity, even the first part, because for finite sets like the set 1, 2, this is exactly what P3a captures as an additivity of the probability function on just 2 members in the union. Okay, but my time is up for today, so that's it for today.